Okay. The AC power flow in linear network. It's the topic of our presentation today. The electric power system. Wait, check this one. What's the problem? Okay, can you see the full screen now?
Yeah.
Okay. The electrical power system now is working with approximately sinusoidal time function. If you have a power system in normal condition, the voltage and current will be sinusoidal signal. So in the general case, we have different condition for the power system. For example, most of the time, the system is in the steady state condition. Every quantities are in the steady state, but we have some transient as well. For example, after the fault, short circuit, we have transient. But in this session, we don't want to talk about the transient condition, just a steady state. So the frequency of the system, the frequency of voltage and current are constant. It depends on the location you are living. You can have 50 hertz or 60 hertz frequency. And for example, in Norway, it is 50. But could you tell me which country has 60, for example, frequency?
United States and offshore.
United States
and offshore.
Okay, and the other country? Can you imagine? For example, Saudi Arabia, Japan, some parts. They have 60, but most of the world they have 50 hertz. But anyway, if you have 50 or 60 in the steady state condition, the frequency is constant. And when the frequency is constant, we can use a new type of analysis in the power system that in this session, we want to focus on that. Anyway, in this session, we will discuss about the complex number because it's the background for the steady state condition and how to represent a voltage and current as a complex value. We'll talk about the impedance, phasor, and how power flow through the impedance. We'll talk about this in this session. The complex values. Probably you had seen it before. Let me use the pen. Previously, you had the digit, for example, 1, 2, 3, 1.5, and the root square 1 is 1. But suppose that if you have -1, this value is a new notation that we used for the complex value. You can see here, you have to remember it. J or I. In some books or paper, use I. In some book, use J, but both of them are similar. So the square root of -1 is called J. And whenever you saw a value with J, we call it complex value. And it is a new notation that we use in the analysis of the power system. And it is the representation in the complex plane. Before, we had just one axis. For example, we had just X or Y, anything. And it was the origin, 0. And for example, it was 1, 2, 3, and so forth. But in the complex plane, we have another axis. We have X, we have Y as well. So with the complex number, we have two axes. One is X, another one is Y. And the X usually called real value. And the Y is called imaginary. Real part, imaginary part. So when we talk about the complex value, you have to consider it consists of two parts, real and the imaginary parts. The real value, it's the axis of real value. And the Y is the axis of imaginary value. And you can see here, Z as a complex value consists of real part and imaginary parts. And here is the real part, here is an imaginary part. And if you want to show the vector on the complex plane, you have to use both axes. And this one will be Z because it's summation of X and JY. It is X plus JY will be Z. So it's the representation of the complex value in the complex plane. It's the mathematical background that you have to know about that, because in future we will talk about the phasor, and the mathematic background of phasor is related to complex value. That's why I started from this point. Complex exponential notation. So the basic for the complex exponential notation, it's the Euler. Probably you have seen it before. Exponential, it is E. For example, we call it exponential. It's exponential A, for example. But if these exponents have complex value, for example, we have J here, we call it complex exponential because the exponent is complex. So the Euler relation is very important, and the Euler is discovered that the complex exponential can be written as summation of two parts, the real parts and imaginary parts. So every complex exponential with the angle phi can be written as cosine function of phi plus j and sine function of phi. It's the Euler relation. We use it a lot to demonstrate. You can see here as well, if we want to represent the complex exponential, you can see, for example, it is Z. It's the vector. It's complex exponential that it has a magnitude is 1. Can you imagine why it is 1? The magnitude of Z. Can you explain, one of you, why the magnitude of the Z is 1? I think I have to first talk about in general case. Suppose that you have in general A, plus J times V. In a general case, it's the complex quantity. If you want to calculate magnitude, you have to get the root square A plus squared B. It's the general formula for the calculation of the magnitude of the complex value. In the Euler relation, since we have cosine and sine function, if we write it, consider this set, put the value here, it will be root cosine square plus sine square. As we know, this summation is 1. And finally, we can say the magnitude of Z will be 1. That's why I wrote here magnitude of the complex exponential is 1. It's the reason. And for every complex exponential, beside the magnitude, we have phase or angle as well. These two parameters are important for us to calculate in the circuit, in the power system. And I wrote here, not this one, but I can show you how to calculate phi. Phi is arctangent the imaginary part, sine phi, and cosine phi. So if you have a complex exponential, you can calculate the magnitude with this equation and define the angle, the phase with this expression. So these two parameters are very important for us. Additionally, these two expressions are also important for us. It's related to Euler relationship. We can show that cosine function of phi will be summation of ej phi plus e minus j phi. And the sine is calculated based off this expression. We can demonstrate it, but both of them can show the Euler relation. Do you have question? Is it complicated? Okay, we go further. And here you can see, we have a general complex value that consists of x as a real part and y as an imaginary part. And it is common they use the small line under the alphabet. That means it's a vector. That means sometimes in different book we have different symbol, but in this reference it means complex value. When we use this bar here, it means complex value. So when you have x plus jy complex value can be written as an exponential, component exponential. We call it complex value, complex number, and we call it complex exponential. They are equal. So, but we can calculate z based of x and y. We can calculate phi based on x and y. And I showed you before that magnitude, it is called magnitude. Magnitude of complex will be root square square of x and a square of y. And the phi's arctangent. Y, the imaginary part over the real parts. And I can show you in the complex plane here. You can see the complex number can be projected on x-axis and y-axis. So if you project the vector z on the y-axis, you can obtain the imaginary part. And if you project the vector z on axis x, you can calculate the real part. So as I talked, this axis is called real and this as imaginary. But some useful mathematical relationship, because we are working with the exponential complex value, some mathematics can help us in understanding, in evaluating the system. So it's better to keep in your mind the product of two exponential. Suppose that you have two exponents, two exponential number, exponential of A and exponential of B. If you do the product, the final result will be summation of exponents. It is useful in demonstration of the relation. And reciprocal of exponential notation. So if you want to calculate the inverse, for example, if you want to calculate 1 over E A, you have to just put a negative for the exponent. For example, if you had 1 over exponential 2 equals exponential negative 2. Product of two number in the general case, these two values doesn't have magnitude. Magnitude is 1. But in the general case, we have Z1 as a general exponential, complex exponential, and Z2. It has a magnitude, phase, magnitude, phase. If you product these two numbers, this will be the result. The magnitude will be multiplied and the phase or the angle will be summed. So when you have two complex number, the product of the two complex number will be in this way. You have to multiply the magnitude and sum the phases or the angles. And the ratio of the two number. If you want to divide two complex value, the magnitude will be divided and the phase or the angle will be subtracted. And we can show that, this relation. And the final is the conjugate. It's a notation that used a lot in the power system analysis. The conjugate of a complex value that we shown in this way. Suppose that we have Z as a complex value, it will be the conjugate of Z. We show with a star here that the imaginary part will be negative. The real part will be constant because Z is X plus J Y. The conjugate of Z, the real part will be the same, but the imaginary part will have a negative sign. And we call it conjugate. And I can show you here, for example, when you have Z here in the complex plane, X plus JY. This vector will be Z conjugate. They are on the same circle because the magnitude are the same, but the angle is minus. For example, if it is phi, here will be minus phi. Okay, so the conjugate of a complex value, the imaginary part will be negative, or in the magnitude and phase, the phase will be negative, but the amplitude or magnitude is the same. Sinusoidal time function. So in the power system, the source, the voltage source, the current source, and the voltage and current through the branch will have a sinusoidal function of the time. I saw you that before in the previous lecture. For example, in a voltage across the resistor, for example, if you consider as a F or V, we can write in this way. It's the cosine function that consists of amplitude, frequency, and the phase. And if I want to show you the plot, here is amplitude, but here is phi is 0 here, but I will show you here better. Suppose that you start from here. This part, we call it phi. It's the phase. Anyway, phase, amplitude, and frequency. It's angular frequency. That is 2 pi f. That is f 50 hertz or 60 hertz. So we can show the sinusoidal function in this way or this way. It's the Fourier transform. If you remember from your previous courses, it's the Fourier transform that you can show a sinusoidal function at a summation of the two parts, sine and cosine, without a phase. It doesn't have phase. It doesn't have any phase or angle. These two ways of representation of the sinusoidal function. However, with the complex mathematics formulation, you can show the sinusoidal function in another way as well. You can show in this way. It's the third way we can show a sinusoidal function. That's any function is a summation of the two parts. It's the complex exponential, and it is the conjugate of complex exponential. So you can write any function as a summation of function, complex function, and its conjugate. It's another form. However, since I can show you its summation of z and conjugate of the z, the final result will be just the real part. Suppose that here z is, as an example, a plus jb. Is it right? Its complex, its conjugate will be a minus jb. According to this formula, if you add z plus z conjugate, these two parts will be added, 2 times A, but these two parts, one of them is positive, another is negative, will be 0. So the summation of Z and the conjugate of the Z will be just real parts. That's why we can use this type of notation for the representation of F. However, what is X here? X bar is the complex value. We call it phasor. In future, I will show you that the phasor of FAT, when we have a function as a FAT, we have a phasor for that FAT. So X is the phasor or the complex number for FAT. So we can show that since it is a complex value, it has magnitude and phase or angle. And you can see here as well. FAT, I want to show you why we use this one. It is X. I take from here. It is X. And we have E, J, omega T. It's this one. Conjugate X is this part. And the E minus J omega T is in this part. If you wrote and sum, you will have this one. You can see similar to this, just the amplitude is a bit different. So you have 2 here, but without 2 here. But the phase is the same. Psi and the phi are similar, but the amplitude is double here. Anyway, I want to tell you with the complex exponential, you can represent a sinusoidal function. And I showed you here that X equals a half, and the psi and the phi are similar. Do you have any question till now? So if you have question, please stop me. According to this definition, the phasor,
Hello?
yes,
I got a question. If you have like the conjugate of, and you have it on polar form, is the same? If you have just the angle, like say minus 45 degrees, would
yeah,
that be the conjugate? Would that be just like positive 45 degrees?
the conjugate will be negative. For example, you mean is that E, J, phi force? Do you mean this one?
Mm.
If it is Z, so its
Mhm.
conjugate, the amplitude will not change. Here is 1, here is again 1. But the phase will be negative, minus J, phi force.
Okay.
Yeah. So anyway, for the conjugate, the phase will be negative, but the amplitude is the same. It is in the form of the exponential. For the real and imaginary parts, in this way, the complex, just the imaginary part will be negative. The real part will become the same. The imaginary part will be negative. Do you answer your question?
Yes, good. Thanks.
Welcome. Okay. The next, according to this definition, so we got familiar with the complex value, the complex exponential value, and how to write a sinusoidal function as a complex value. So I want to present new notation in the power system. We have impedance. Before that, you had a resistor. and you had resistance. However, in the power system, we have inductor as well. We have capacitor as well. So if you want to evaluate the performance of a capacitor and the inductor, we use new notation that we call it an impedance. Impedance in general case can have two types. It can be inductance. It means that you have inductor, or it can be capacitance. You mean that in the circuit you have capacitor. But the impedance is a general quantity. Since it's easy to differentiate a complex exponential, we use this notation. Do you remember for the inductor, you have L. If you want to write the voltage, you have to use this expression. The voltage of the inductor is L derivative of current. It is current of inductor, and it is the voltage of inductor. So the voltage and the current are related based of this expression. You can see we have derivative here. Sometimes solving the equation with derivative is very difficult. However, in a steady state condition, we can have some kind of handy trick that can be used for the analysis of the circuit. That in future we call it phasor analysis. In any way, we can remove this derivative and make analysis simpler. You know, it can be interesting for you to have this one. For example, in a circuit, in the power system, you have a voltage, and any voltage, it's the sinusoidal function, and any signal with the sinusoidal form can be written as a summation of the complex value and its conjugate. And in a similar way, for the current, can be written as a complex value at its conjugate. So we know that from our previous slides. However, I can show you that voltage is related to the current with this simple relation. These two expressions are similar, but here we are working on the time function, or here we are working on the phasor. V is a complex value, or its phasor. I here is the complex value, and this one, J omega L, that we call it impedance. It's the complex value. So we can transform all analysis we had in the time domain to a complex domain. Anyway, instead of time function of voltage, we can use exponential, the complex exponential for voltage. Instead of currents in time, we can use complex value. And instead of, for example, resistance, we can use impedance. So we have some kind of duality between the time and the phasor, between the time and the complex plane. So you have to remember this expression. For every inductor, we can define impedance. And for the inductor, the impedance will be J times omega times L. And omega is 2 pi phi. It's related to frequency of the network. is constant, 50 or 60. So suppose that instead of this difficult expression that we have derivative, we use just this. So imagine how comfortable it will be, the analysis of the power system. So, but you have to remember this analysis just used for the steady state condition, not transient. Just for the steady state condition, we have no fault, we have no tripping, we have no disturbance in the system. We can use this type of analysis for the power system. Okay. So, and we have the same notation for the capacitor as well. You can see it is the capacitor, and the relationship between the current and voltage of capacitor can be written in this way. Is the derivative of the voltage will be the current. However, solving this equation is difficult. Instead of this, we can use the impedance of the capacitance. And what's the impedance of capacitance? It's the impedance of a capacitor. So it's 1 over J omega and C. So whenever you have a capacitor in the circuit, you can use the impedance of the capacitor. And what's the impedance? It's 1 over J omega C. So always remember this expression, 1 over J omega C, and another one is J omega L. It's used for the inductor, and this one is used for capacitor. These two expressions are very important in future to evaluate the power system during steady state condition. So do you have questions till now? If not, we can go to have a small break and then we will return. Okay? So I have to stop recording.